Okay, so I minimize this so it will not take much space. Okay. Okay, so hello everyone. So yeah, Mahdi, and thanks for the invitation. Happy to be here and give you this talk. So today, I'm going to talk about kinematic redundancy resolution in wearable robots. Yeah, I'm currently, like, recently I became the maître de conférences at Sorbonne at ISIR. So my slides, okay. So yeah, so I'm part of ISIR in Paris, and my research interests are like from physical human robot interaction, which was mostly like my PhD work, and then during my postdoc at ISIR, I was working on assistive technologies on wearable robots that I'm going to talk about today. And currently also I'm working on robotic manipulation. So to give you a quick outline of the talk that I'm giving today, so I picked like three contribution that I did recently on which all evolve around kinematic redundancies. The first one is I'm going to talk about prosthetic robots, and then I'm going to talk about kinematic redundancies in humans, and finally I'm going to talk about control of a supernumerary robotic arm. So so prosthetic arms. So the challenge is mostly on the control side. So here is the video of the recent Cybathlon competition. Here is the smart arm from Sorbonne. I'm taking no credit for this work. I'm not part of this. So there are like amazing and very advanced mechatronics for to enable Christophe to perform this task. But if you look at the movement of the elbow, for example, which is actuated, we see that the elbow does not move so much. And it's mostly a problem of control, of interfacing with the user, which most of the control strategies to date are using the myoelectric control, trying to decoding like human intention from surface EMGs, which is a very limited and hard problem. And so this kind of limitation of this method made people think about other approaches, which we call them like movement-based controls. Because okay, if the device is not reactive enough, giving the redundancy of the human body, all these joints that we have, for example, the hip will try to perform the task anyway. So one idea is to kind of look at this body movements of the user and trying to figure out what the human is trying to do and trying to help the human with the task. So this is a previous work from the lab, which was based on this concept of compensation cancellation control. So here the user is wearing IMUs and they're tracking the user's body. So whenever the user is trying to do a motion which is not comfortable and trying to bend, sorry, I cropped the video in a bad place. Uh, the control of the rest is gets activated. So in a way, the intention recognition is based on unnatural posture. So I try to like what I'm going to present is a way to develop such control strategies that not only relies on the posture but also on the movement. And the idea is to help the human to maintain an ergonomic posture and also restore the natural joint inner joint coordination. Also to show that this kind of control that we're proposing are stable. So before starting, just to a bit of notation. So yeah, so we have the forward kinematic as we know it, the mapping from n dimension to m dimension of the task, and then if we have more joints than the end effector, for example, position, then we say okay, we're dealing with a redundancy, kinematic redundancy. And for the instantaneous forward kinematic, we also use the Jacobian, which maps the joint velocities to end effector velocities. And this, when we are redundant, the matrix is not a square. Simple stuff. And then for the inverse kinematic, we have infinite solution. We can formulate this infinite solution using the general inverse of the Jacobian. Here is noted by J pseudo inverse. And any pseudo inverse that satisfies this property is can be a solution, and we can plug in any knowledge space velocity that we want, and it would not affect the task. So one practical choice that we use in robotic is the weighted pseudo inverse. And so we can also show that it's simple to show that this is a solution for this minimization. And people sometimes, if when we don't know what to do with W, we usually put identity weight, so it does become the right pseudo inverse of J. So to go back to the problem of the prosthetic device, the control of prosthetic device, the way that I formulated the problem, I used this leader-follower setup scenario. For example, here we have a three-joint system, and we consider that the task is a planar robot, so the task is two-dimensional. And here I call that, okay, the leader is controlling the first two joints and the follower is controlling the third joint. And so the forward kinematic, it's nothing special. It's just that we can dissect the Jacobian into two parts for the leader and for the follower. And then we assume that the leader is trying to go somewhere. So the desired velocity, I write it as VL. So this is something that only the leader knows. And he's trying to go to, so this is the end effector position. It's trying to go somewhere with some gain. And we assume that this system is trying to minimize the cost. And there is also a posture that is, for example, we want, for example, the hip to be upright, for example. So there is also, we know, a preferred postures. So again, so if the follower knows already this intended velocity by the leader, then the solution, we can write it as a centralized solution. So as before, we just plug this W that we have into this, we compute the pseudo inverse and the knowledge space projector. So I start writing the pseudo inverse in this form, a dissection between the leader and follower, also for the knowledge space projector. This segmentation would help us later. But anyway, the solution is as before. It's nothing changed here. But given the fact that the follower doesn't know the intended velocity of the leader, so now we see how this segmentation helps. We can write two lines of inverse kinematic, one for the leader, one for the follower. So leader knows its intended task, so it follows it. But the follower doesn't know this, and we replace it with this VF. And VF is actually a filter version of the end effector velocity. So what's happening here is that the leader is trying to do the task. It moves, so it knows the VL. It moves its joints. It creates some end effector velocity. The follower would look at those end effector velocity, and he will try to kind of replicate or amplify it. So this simple amplification, we'll see that it's very effective and actually very stable. So to kind of show the dynamics that arises from this kind of formulation, I give you a simple example of a 2D task. Two degrees of freedom with one-dimensional task. There's like two prismatics, so forward kinematics, and then the weight matrix. So I didn't mention, but the weight matrix, what matters is the ratio between the two entities. So we always can assume the first one is one, and then there is just one parameters that parameterize this controller. And the knowledge space velocity, we assume that the leader or the first joint wants to go to its rest length, QL equals 0. And the inverse kinematic of this system would be very simple. It's like if you define lambda as 1 over 1 plus WF, and lambda bar is the 1 minus lambda, the pseudo inverse and knowledge space projectors are very simple. And if we replace those into the equation that I showed before, we arrive at the dynamics of this system that are like this. So here we can already study the effect of these parameters that we put here. And this parameter WF, it means that how expensive the follower is. So if we have a very high WF, it means that the second joint should not move, and all the tasks should be done by the first joint, and the opposite here. WF equals 0, it means that the second joint is really cheap, and all the tasks should be done by the second joint, by the follower. So here, if we replace lambda equals 0 into the dynamics, we arrive at something. I drive at these simple dynamics where the follower doesn't move. So the follower is not providing any assistance, but the VF will converge to VL. So we have intention recognition because the follower understand what the leader is doing. So we have no assistance, but we have perfect intention recognition. On the other side, if we replace lambda equal 1, we see that the leader is not doing the task. So there is no VL. He's just trying to go back to his preferred posture. VF becomes minus VL. So the follower understand, okay, so first, maybe third one. So v dot f stays where it is. So since we initialize at the 0, so vf always stays at 0. And so the follower understand the task is to stay stationary and just tries to help the leader to go back to his preferred posture. So here we have assistance, but we have no intention recognition simply because the leader never showed any intention of a movement. VL, who the term that was here disappeared from the equation. So here already we see that in this kind of leader-follower system, the intention recognition and assistance are kind of contradictory. We cannot have perfect assistance and perfect intention recognition. And if we write the equation in the middle, I don't drive the equations here, but the equations can simplify to this. And this QF star is the solution of the centralized system, the one that I showed on the previous slide when follower knows VL. So we see that the solution of the follower can converge to the centralized solution if these guys they converge very fast if these guys are big. Alpha is the filtering rate, so we want very fast low pass filter, but we cannot increase it in practice because it will lose robustness. And we want this guy lambda war to be high, which means we want lambda to be small. But okay, if we increase it too much, we go to this case. Okay, we will have a good convergence to the centralized solution, but it's a centralized solution where the follower doesn't help. So this term they should be tuned kind of rationally to have a good behavior, kind of a good balance between assistance and intention recognition. So here is the simulation result of this simple system. Uh, so yeah, so this is the centralized solution is showed with gray. It's like they're supposed to go to 1, and the leader is supposed to go to 0 and at its rest length, and the task needs to be done by the follower. So we see that if we pick a WF which is 0, which means the task should be done by the follower, the task will not be achieved. Only the follower only helps the leader to go back to its rest length. So we see, for example, if you pick I don't know, like the green here. So if you pick a small WF, which means okay, it's the follower is cheap, but it's not 0. We see that the solution, the green one, the solution very resembles the solution of the centralized solution, which allows the leader to go to its rest length, and the task is actually being achieved by the follower. So this can be also like formalized, like quantified, this behavior that I showed. We can take the differences between the solution that is here with the centralized solution in the task space or in the null space here, because the null space is actually the joints of the leader, or in the joint space here. And we see is the same story. So for the task, if we want the task to be done nicely, we should not rely so much on, we should not completely rely on the follower. We should accept that the follower has would not do. We should increase the WF. We should move in this direction. And if we want the null space to be done, we should leader should not yeah, so if we want the null space error to be small, we should be to this side. So this is the minimum. We want to move this way. Here for this first one, we want to move this way. And if we look at the joint space, we see that the solution is minimized somewhere around here. That the solution really resembles the solution of the centralized case. So here, so far, I made an assumption that when these systems they work, the leader and followers they have an agreement on the WF. We can have systems where the follower and the leaders they have different expectation for WF. So here is the WF that the follower assumes for itself, and here is the WF that the leader assumes for the follower. So immediately we see, okay, so the graph is the joint level error. So this is this error that we are trying to minimize. So first we see that if leader says, okay, follower, you should do everything, regardless of what the follower does, we will have a very bad performance. Also, if the follower assumes that it's him who should do everything, it also doesn't lead to good behavior. But we see that we have a nice like a valley here of solution, which actually what we need to do in the system is that the follower says, okay, I'm going to contribute, but at the same time I'm going to rely a bit. It's like, okay, I'm gonna pick some WF that are, I don't know, a bit below that zero point 0.5, and I expect that the leader also would move and show me the intentions, and then I'll try to contribute to what the leader is doing. So this is the same similar scenario, but instead of the two degrees of freedom, it's like the planner robot that I showed before. So here we see the same thing, like in the centralized solution. So the goal is to go somewhere with the end effector. So we see in the centralized solution the solid lines. The hep doesn't move because the null space is that we stay. So this is the preferred posture, and there is only a gain here. So it means that we want to stay upright. So we want to achieve this task without moving the hip. But in the leader follower, or when is this like a prosthetic joint, what happens here is the leader is moving his hip a bit to kind of shows its intention, and quickly the third joint, the follower, picks up the intention and trying to perform the same movement with a bit of delay. This is like a delay that takes the leader to convey its intention. So the leader does something. So the leader kind of sacrifices a bit his null space or his posture to tell the intention to the follower. The follower picks up the intention, and then it can go back to its stress length. And the performance of how, if they should agree on how they should agree on the contribution of the follower is the same behavior as before. So I tested this on participants, on human subjects. So I designed this kind of game where I track the subject's movement. So this is actually, I picked this point to really create the same 3D three joint planar robot, which we see on the screen. So I tracked the human behavior, like kinematic behavior, and I showed them a goal to reach on the screen. But the third joint, I controlled it in different ways. So this different ways, okay, one case is that the human is controlling all three joints. The second case, the elbow is fixed, so they have to do the task with the only two joints that they have. The third case is called, like I call it synergy, is something that is used a lot in the literature. That, okay, if we lose control of a third joint, we just copy of the velocity of the shoulder to kind of create opening and closing behavior of the elbow. So the proposed controller is here, but at the same time, I use this opportunity to test to see, because there are two terms here. So I tested to see if the performance is mostly thanks to this part, which I call it like a synergic part. So I wrote this here, and or is it mostly because of the correction in the null space? So I kind of I separated these two parts and I put them as condition as well to know better how the system works. So this is the demonstration of these controllers. And so for example, here we can see that on the fixed elbow, we see a lot of like hip movement. It's expected because the elbow is locked on the screen, and we should move the hip a lot. But if we kind of pay attention, we see that here we don't have so much like hip movement, and the user is able to control the third joint kind of intuitively. We see sometimes, for example, the synergy is a bit struggling, and so yeah, so I this for 10 subjects, and so I get some statistics. I analyze a lot of like metrics, but the only metrics that give me something concrete and positive was the hip utilization. So I compute this as a baseline with the case where the human controls all three joints. So first we see that okay, synergy is already improving over the fixed elbow, but the control that we propose here it's really reduced the hip utilization. So this summary is the first part. Uh, this controller kind of manages to recognize the human intention from the posture and the movement. So here, kind of by this statistic here, I kind of show that it helps to maintain your ergonomic posture, but this question of restoring the natural inner joint coordination, how this joint moves with the other one, is not really answered here. The stability, I'm not going to show it here. I refer you to the paper. It's half a page. It's a simple proof of stability of the dynamics that I showed earlier. So yeah, so then I kind of followed up on this question of how we can restore natural interjoint coordination of a human. So for that, it's like we can ask the question, okay, can we have a better metrics of how joints coordinate with each other to perform this kind of task? And at the same time, these WF that I had, they were like set experimentally. So I had to also think about how find the good like values for these WF, maybe by looking at humans. And so which leads to the third question that I put here, that if as human we have kind of an underlying like weight matrix in our inverse kinematic behavior. So this led me to the second contribution, which was published like last year. So to specify a bit, like inner joint coordination we usually refer to as like how the joints move together, and in the literature there is huge body of works that they perform kind of correlation analysis, which means that they ask humans to perform some tasks, and then they take the joint values, and then they try to find relationship between these time series. Analysis such as like synergy, PCA, or singular value decomposition, which is basically the same thing, or grandeur causality to see which, for example, joints value cause the other one. And so here I like to like quote this sentence from Ratesh, who's apparently like fed up with all these correlation analysis, and he's actually one of people who propose like some model-based approaches. So the difference is that is here is like we don't say okay how joints they move together. Is like we also consider what are these joints are trying to do, what are their goals, and by doing this we try to bring some models into the pictures to try and just to better understand what the joints are doing together. And maybe the big example is actually from Latosh again, is like uncontrolled manifold, which is kind of analysis of variation, because he uses the Jacobian matrix to kind of divide the control into the task space and knowledge space, and by doing this he also dissect the variation into task space and knowledge space. And for example, then you can compare to see which dimension has more variation, and by doing this we can make a statement about human motor control. uh, but at the same time it doesn't actually like kind of answer the question about like inner joint control in the sense of the test that I showed before, where we want to kind of quantify human like like inverse kinematic strategy. So for me it was more a question of how these joints contribute to move the end effector. And actually the motivation is that this answering this question would be very helpful for rehabilitation and prosthetic arm that I showed before, and any other system of type of leader follower setup. So coming from the previous work where I use inverse kinematic, like pseudo inverse weighted pseudo inverse kinematic, is not so surprising that I was thinking of using the same model to model the human kinematic data. So yeah, so the difference is that, okay, we have forward kinematics, inverse kinematic, but the problem identification is that we have this pair of x dot and q dot, and we want to figure out what is the weight matrix and what were the null space velocities. And already this is kind of in general, it's an ill-posed problem, because every weight matrix that we pick, it provides a different decomposition, which is kind of valid, because okay, so this x dot and q dot are given, and we pick a w, it gives us a pseudo inverse, and we project this. We say, okay, we call this q task and null task, and this, the sum of these two gives us back this q dot. And we can see that. So first I give you an example. So imagine that we saw like these two simple two joints, the two prismatics, that they were moving like this. The first one was stationary and the second one was moving. And if someone assumes that their weights were equal, so the Jacobian pseudo inverse should be 50%, 50%, then the composition that we have is something like this. It means, okay, they were supposed to move because they were supposed to move equally to create this 1 meter per second, but actually they were doing something in their null space. The first one was trying to go back to, and the second one was trying to go forward. And if someone else picks a different like weight matrix and arrives at different pseudo inverse, they can also justify this. Okay, they were not trying to do anything there like so much in their null space. It's just that the task was supposed to done by the second joint. So any w would fit to this data. So if there is no modeling error, we are screwed. And the reason is that whenever there is any possible modeling error is kind of vanished in the null space, because whenever we cannot do with the first thing, we put it in the null space and it works. So the trick that I use is that, okay, then let's not rely so much on the null space. So the velocity that I pick from the null space, I multiply it by some kind of a gain. I don't know, I pick just 80%. And then doing this, I have some kind of an error model, which allows me to kind of optimize for the weights. And so this is maybe the most heaviest equation heavy slide of my talk, so bear with me. So yeah, so I start with a data set of observed kinematic. So I observed this kinematic chain. It gave me a data set, like k data point of joint velocities and Jacobian and end effector velocities. Kind of, this is a bit redundant, but I put it anyway. So the formulation that I use is this. So I say, okay, if at any time I start with estimation of weights, then I can have a pseudo inverse. Then I have null space velocity. So I change my notation because I need the subscript k here. So I have a null space velocity, and then this gives me an estimation for the joint velocities, and the difference between these two is the error of my estimation. And using this, I can move this. So using this, I can drive an optimization problem. So this is just I'm just replacing j. So I'm taking this equation here and I'm replacing pseudo inverse and null space velocities. So I arrive this equation. Then I can replace the estimated velocities with the actual one. So I get the error on the other side. Then I multiply by this w that is here. So I like this w on this side because this part is linear with respect to w, and the annoying part that is nonlinear with respect to w, I keep it on the other side. And then this is a term that we can just define it as uk, yeah. And then now here, this was for single data. I can concatenate all the data that I have and I write it in a matrix form. So this is the matrix form of this equation where all the data is used. Here I wrote the dimensions of these matrices, and then so he can see that these dimensions are big, because if you have, I don't know, 1,000 data points, this is not easy to handle. So what I did is just I multiplied by the q dot transpose. This brings me to a lower dimension. So this set of equations, they become something very simple with on the lower dimension, that the parameters that I want to estimate are here. They're also hidden inside here, but they're hidden in like it's this term. They're hidden in a nonlinear form, and that's why. Before that, I also, what I would like to do. This is a matrix. This is a diagonal matrix, and I can rearrange all these matrices to make it into a W, which is a vector here. So this is something that I want. So this is becomes really like a linear equation, like our ax equal b that we love. So it becomes a simple linear system, and the parameters that I like the parameters that I want, they're here. They're also hidden inside this matrix, which is originated from this term. But I don't care. I will solve this equation in a quasi-static way, which means that every time I try to minimize this error using this W, and then I'll update and I solve again. So this arrives me at this quadratic programming scenario where I try to update the weights. I want the weights to be between some range, because these weights I would like them to be between 0 and 1, and maybe a bit above 0. So yeah, so I use this. So I formulated this problem of identification in a sequential quasi-static quadratic programming. So I repeat this process until these W's they converge. So yeah, so first I'm going to show some. I'm going to show the result of some random data set. So I picked like a simple case where there are three. There are three. The task is three-dimensional. There are 5 joints. I generated like 5 data points in a completely random way with some known weights that are like descending from one. And this is the result of the optimization. They converge to these values. I repeated this many times to get also this confidence interval. So the result is satisfactory. And here I studied the effect of gamma. That was the term that I use to rely on the null space or not. So we see if you rely too much on the null space, the weights they don't update. And the lower that we have, the faster we converge. So someone might say, okay, let's just not rely on the null space. It would converge very fast, but we should not forget that this data is IID. In cases where the task and the null space are correlated, this actually doesn't work very well, and we see it in actually this case. This is the data from a prismatic, a two prismatic, and we see that if we say that there is no null space, actually the solution would not converge. The solution, they converge when we are not one, but very close to one. We're sure that we have a good convergence, but the convergence is slow. There are some usual trade-offs of tuning this parameter. If someone can, I don't know, we can use decaying like gamma, and we converge to good values. And anyway, this optimization is very fast. This problem is very low dimensional, and there is no computational like cost here. Actually, it's a very, yeah. So, and to kind of verify this on real data, I used the data set that was kind of collected in the lab before. It was like subjects that they were like performing tasks wearing like an exoskeleton. So the task was to reach for these goals that we see here, this 1, 2, 3, and they had to repeat this task, and they were wearing this exoskeleton, and they were different. They were exposed to different like viscous fields. So this is the idea is to see how the humans they adapt to kind of perturbation that are applied to their body. And so there were like so there are two cases that I use. There is one natural, which is they were wearing the exoskeleton and there is just gravity compensation, so they don't see so much effect of of wearing the device. And the other case, there was a like a vector, there was a viscous field that were applied to force them to use different solution for during the reaching motion. So this is kind of the data of average over all the subjects for different tasks. We can already see that, okay, between like blue and red, there are some differences here between these two, and there are some like differences here, but it's okay, we see it on the data, but it's really hard to like quantify this using the synergy methods or the correlation analysis that people are using in the literature. So if I apply the method, the identification method of these weights, we get the weights. So there are four values, like there are a weight for each joint in the two condition in the natural and the viscous field. So first, what I notice is the first joint is kind of over specified, so it's not part of the is not part of the redundancy. It's always needed for reaching motion. So I that's why I set the weights to one. And then we see that the is like not this the first joint is the first joint that is the most costly joint, and the second joint doesn't change so much, but the changes in the third joint, which we see a statistically significant difference between the two conditions, which means that like in the viscous field, the third joint became more costly, and this is like in accordance with the actual viscous field that they're applying to the human subjects. Okay, at the same time, it's nice, but it's hard to interpret, like at the to understand to compare these values. So I kind of did it like an inverse of this. We compute like this beta, we call it, I don't know, contribution coefficient, like who's doing the task. And we see that in the natural condition, like 60% of the movement of the end effector was generated by the third joint, by the shoulder flexion extension, while in the viscous field, the role between these two joints kind of changed. So now the task was just done mostly by shoulder interior exterior rotation. So yeah, so it provides a nice way to quantify the human inverse kinematics. And so this is also when we have the W's, we can also look at the null space velocities. So we see actually like when we estimate the W's, there's actually not so much difference in what the subjects were doing in their null space, which actually if we rely on just W equal one, and then we look at the null space velocity, we start to see like this kind of effect, which might mislead us, that we might think that actually the humans that were not changing their inverse kinematic strategy, but they were just trying to do something different in their null space. So actually, so it kind of shows that analyzing null space velocities between conditions is not so safe when we're not estimating the correct uh, weight matrix for that specific condition. And also, this is also the same analysis applied to the data that I showed before on the leader follower of setup of the prosthetic device. And so here, which shows that so it's better to look at the table. It shows that in the natural condition where the human subjects they control three joints, like 98% of the task is actually done by the elbow. And then when we lock it or when we use synergy, it's not that we have so much movement restored, but then when we use the assistive case, like 80% is restored. So it's good news. So okay, so the summary of this part is that okay, I propose some method that to study the inner joint coordination that looks at kinematic data. It tries to model it with the weighted pseudo inverse, and then we arrive this IK weights that we can claim something about the joint inner joint coordination. We can either pinpoint differences across condition like the viscous field that was applied to subjects, or we can talk about restoring a specific IK strategy like in the case of a prosthetic device. And also it's good a statistical tool because we compress the data a lot, so it gives us robust statistics. Also, just a note, is that in this work we're not claiming that the human brain is actually solving like weighted inverse kinematic problem. It's just a way of modeling data. So the third part, I don't know how much time I have. I think I have 10 minutes, so I try to quickly show the control of a supernumerary arm. So yeah, supernumerary arm motivation is that we want to enhance human capacities. Like we want to do like improve human strength or precision or versatility. And there are challenges at different levels. For example, at the low level, we think people are working on mechatronics and making these robots more lightweight. At the high level, people are trying to find ways of interfacing this with human brain, with human muscles, or giving it like cognitive capacities. But so the work that I'm trying to present is mostly in the mid level, where we are trying to do like motion planning and solve inverse kinematic and physical interactions. So yeah, so this is Kinova robot, worn by user on this homemade vest, and the power and the controller off board. And so yeah, so the idea is to have an IK solution that satisfied several things. For example, first it should follow what the human wants to do with the end effector, and also it provides like compliant interaction with the environment, and also provides like safety consideration, for example, not colliding with the user or generating high impacts. So this is kind of the architecture that I use. I have the we're having the robot state. We can have some software safety on several like aspects of the robot's movement, and then the idea is to kind of embed all these safeties into like quadratic programming constraints. And this will be a node like running on in ROS. It will receive what the desired robot task, and then it provides the task execution, safe task execution. At the same time, we also rely on the like a low level controller of the robot for cases where there are hard collision, and we have to shut down this. So when we don't, I mean, as a reaction strategy, when we shut down everything, we fall on the very low level admittance controller which is implemented on the robot. The fact that for example, that the robot is back drivable and provides some lower level safety. So this is like the formulation of the controller. So this is like u is like the decision variable, the joint velocities that we will command to the robot. The inverse kinematic is here the first constraint. This is like the slacked version of the inverse kinematic. Here we allow the robot to slightly deviate from the task, but with a respective cost. And the task is also like there's two parts. There is the part which is commanded by the human, and there's also the part that comes from the admittance, which will deliver the physical interaction. There's also a part, the linear part is also there to kind of help us to maintain a knowledge space preferred posture for the robot. And so we have the inequality cost, and here as it's shown, and the idea is to incorporate safety consideration into this inequality constraint. So for example, the first simple one is the joint velocities directly goes the into our inequality constraint. For the joint position limits, okay, everything is written on velocity. So if you want to limit the joint position, we have to kind of take the derivative of this side, and which means like, and we also have like a conservative factor here. Delta t is the control rate, but for example here you say for example when p is 10, we say in 10 future data time steps we don't want the q to go below q minimum. So we can also simply put the joint position limit. This is something like classical, everybody's doing this, so there is no trick. Also we can limit the power of the robot. So this value is actually we picked it experimentally, because if for many of these things I try to follow the ISO specification for the ISO specification of the power is something around, I guess it's around 40 watts for the robot. But we try to operate robots like in a range of motion and interaction when we saw, okay, 4 watts for this quantity, because this is what they talk in ISO is the input power of the robot, like the electrical input power. But we saw, okay, for this term, which has also the the, the nature of power, 4 watt would be enough. So we set that experimentally. And for the workspace, we just put a bounding box around the user head and torso, which is kind of specified with this limits of XYZ. And the good part is that because the robot is fixed to the body, so they're not rotated. So it's simple, uh, like linear checks like this. So here we say, okay, so we also do this for many points on the kinematic change. So we say for any of these points in the next k time steps of the control, giving the velocity of that point, we don't want this point to penetrate into this boxes. So each of these guys, there are three-dimensional XYZ, and 2 times for penetrating from left or right. And then we can also use the partial Jacobian to get the velocity of each of these points, and we arrive at these inequality constraints, which we can integrate into our quadratic programming, and it provides behavior that is shown here. So the user is applying some desired velocity, which is shown here in blue, and the green one is actually the one that is computed by the QP, which doesn't allow the user to penetrate into these boxes. So yeah, so you can go all around the user without penetrating into these boxes. And this is just the quantification of this behavior. So here we commanded the robot to go. We wanted to move actually linearly from, this is the end effector, we wanted to move linearly to this point. So the robot took this pass, and we see that all the joints are planned in a way that they don't penetrate into the boxes. And this is the associated joint position and velocity, that they all are respecting the constraints. Uh, Interaction is just basically the admittance control with a dead zone. So I skipped this for time. We also studied the interaction forces. We put the robot into the contact, and we slowly increase the commanded velocity, and at some point we go out of the limits of the interaction forces and joint works, and we trigger the low level control of the Kinova. Here is the impacts. So the robot is in free motion and impacts into a surface, into a hard surface. Actually, a external force torque sensor where we can read these forces. So we see that if we like collide into a surface with high velocities, the robot would turn off, and the robot starts to bounce on the surface. The power exchange between the robot and then the surface, actually for some very high velocities, like goes out of the limits of what we wanted. But anyway, this is like the robot is kind of, the control was taken away from the QP. There is not much that we can do here to limit this. It's actually a limitation of this way of controlling. Basically, we have to think of better reaction strategies for impacts, but still take like picking this very conservative 4 watts. This is still like not so. This is manageable by I think by ISO standards. I didn't do extensive study on this. It's just the limitation that we know about this work. So yeah, so at the end, so we have a unified QP-based controller that provides the task execution, physical interaction, and safety. So I'm done, and this is just the summary of the three contribution that I talked about. So in the first part, I talked about treating prosthetic robots as the leader follower setups, where we try to do intention recognition from partial kinematic observation and provided assisted behavior. In the second part, we use Semlar's formulation for modeling kinematic data, which allows us to talk about inner joint coordination and compare kinematic strategies in our experimental scenarios. And in third part is I showed like this safe IK control. And but actually the third part is still kind of like disjoint with the other two because we didn't get to the point. Still, we're working on a way of commanding this robot using huge like movement based control. So this is kind of the future work. And I thank you very much for your attention. I'll be glad to hear your questions.
Thank you, Mahdi. Yes, we have some time for some questions, I guess. Vincent, I see your microphone is open.
Yeah.
I,
Merci Mahdi pour la présentation.
No.
Yeah, I have a question about well, it's more of a comment because I'm getting old, so I'm making comments more than asking questions. But about the work on identifying W, I tried to do that long time ago using some learned motion. So we were like learning some Jacobian using LWPR and trying to get from this data W. Quite exactly the same equation you were using, but not identifying it the same way. And what we noticed with the W we got was that sometimes it made sense. Like we would see one joint actually moving a lot, and the associated weight being related to that to this absence of motion or to this lot of motion. But sometimes it would not make sense, and it appeared, or we felt like it was related to the fact that we were, for example, close to a limit, a joint limit, for example, and this framework does not capture this in essence. And I wanted to have your, I mean, to be honest, I didn't read the paper from 2022 that you mentioned, and actually I should probably. But can you give us your comment on how important or not important are these limits to be accounted for in this identification?
I mean, in the paper, actually, I discuss about the joint limit, which is kind of the method is kind of it's kind of robust to it. Because I mean, at the same time, if you have a kinematic chain and a joint is always close to its limit, it's probably is also it should have some high weights, right? Because it means that it's not contributing anything to the task. So the problem, I don't know, you were getting like a low W for it, or
no?
Because
no,
the other thing, the huge assumption that I make is that I have the Jacobian of the kinematic chain, right?
Okay, yeah.
Because you were saying that you were using methods to even estimate the Jacobian.
Yeah, we were doing both.
So
yeah, the point is also that we were not trying to identify W like a compromise over all the motion, but we were looking at W instantaneously in different situations to see whether this W was correlated to what was going on at that time, which is a bit different from what you got. But I agree that W can capture in some way the fact that you don't move because of your joint limit, but maybe it's a bit limiting to consider that W captures all of this in some way.
No, definitely. I mean, that's what I was trying to say, that the human brain is not trying to use like weighted pseudo inverse kinematic. Yeah, I mean, you might when you get a high W, you don't know why this W is high. Either it's, as you were said, it's close to joint limits, or it's just that joints, I don't know, you're tired, you don't want to move that joints, or it's just a task, it's, I don't know, it's obstacles in the environment. It's that's why it's just a tool to compare. Like for me, it's just a way to compare two conditions that are very similar and then try to capture like small differences in kinematic strategy. It's not, we cannot do we cannot talk about like really the inverse kinematic of that particular subject at that particular moment in that particular condition. It's a hard question. At the same time, trying to like solving W's over time is also it's a hard problem. I tried a bit. It's not easy. I mean, because we kind of use a statistical power at the same time, right? Because I use all my data to just identify, I don't know, for example, 4 W's. And if I have to do this for each time step, it's like I don't have a statistical power. And
Yeah,
at the
no,
same time, it's really hard also to maintain a meaningful profile for the W's. I mean, that each W that we get are close to the W's in the time step before and after. So it's a very hard problem.
yeah, we had this kind of switch between two time instant where the W's wouldn't look like the same, and that was hard to compare actually. But yeah, anyways, it reminded me of this work. But I think it's a very good tool to capture something complex with just a few numbers. So just wanted to comment on the fact that I like it. I don't know whether that's the way to go, but I really like the
You should
approach.
send me the paper. I mean, because
it was a first year master's report, which I gave up after. I said, okay, that's. I tried. It's nice, but I don't want to keep with this. But I can send you the report. It's in French,
thanks,
but I guess it's easy
it's
to understand.
Yeah.
So I will send it to you. Yes.
Okay,
but anyway, thanks for the presentation, and I like the very frightening videos about the mounted arm on your back.
Yeah. I mean, I know you're tired of it because you're now seeing it many times with.
No, I'm not tired of it. Actually, I remember trying it with Jacko. Nathaniel put it on my back a few years ago, and even if I am a big guy, I didn't feel that safe.
No, it's heavy, and it's also like the problem. I mean, Nathaniel is trying to make a new vest, but the problem is like the weight is not balanced. So you start to like pull you, and the vest is trying to like choke you. Like it.
You should have a second arm doing the opposite motion on the other side.
Yeah, there are some people like there is a project going on like started recently with 4 arms. So someone wants to do Dr. Octopus. So
yeah, exactly. Okay. Anyway, thanks for the presentation. It was really nice.
Thank you.
Thanks for the presentation. Do we have other questions? Okay. I think we are exactly on time.
Okay.
So maybe we can close the session.